Good afternoon, everyone. So let me first thank the organizers for inviting me to speak. I really enjoyed the conference so far. And so my contribution is going to be talking about how we model astrophysically relevant shocks in laboratory experiments. So kind of what we can do, what we're able to study, at least at the moment, and maybe where we're going in the future. Let me first thank all the collaborators who've helped with this. This is, I'm going to present on sort of several related projects. So it's been a big team. They've been tremendously helpful in carrying this out. So the basic approach here, I'll give a very brief background on collisionless shocks in case you stumbled into this session for the first time this week and didn't hear anything from earlier today. And then I'm going to talk about our general approach to creating non-relativistic collisionless shocks. So I do want to give that caveat. It's non-trivial to go into more relativistic cases. We can maybe talk about that towards the end. And then the ongoing shock projects, at least the ones that I'm personally involved with, I'll talk a little bit about others, what we can create in the lab and what we can study from those. With a focus on, in particular, two overarching questions around energy partitioning and particle acceleration. So basically, the modern era of collisionless shock studies in the laboratory began about 20 years ago. And so we've seen a lot of progress on this front in various types of collisionless shocks. The easiest ones to create in the lab, because they don't really require anything but a laser and a target, are electrostatic shocks. And so we saw those first in kind of the mid to late 2000s. That's kind of shown here. The kind of next easiest in terms of experimental setup, though it turns out to be very hard in terms of the physics, are what we might call electromagnetic shocks. So these are shocks that don't have any pre-existing magnetic field and have to self-generate them in some way. So the most well-known one are these Weibull-mediated shocks. And this is an example from some experiments that were done just a few years ago on the National Ignition Facility. And then if you add a magnetic field, this makes your experiment much more complicated. But it does allow you to get to magnetized collisionless shocks, which are the ones that we're going to be most interested in for our purposes, because these are kind of the most prevalent ones that we see in the universe. So I'll focus on this, but I just want to highlight there's been a lot of work on different types of collisionless shocks happening in the laboratory. So just to orient everyone, so this is your basic outline of what a magnetized collisionless shock looks like. This is a profile in B. It might be similar for the density. And a couple of things I want to highlight because it'll come up later on. So one, you get sort of different types of profiles depending on whether your shock is propagating along or perpendicular to a magnetic field. So you hear me talk about quasi-parallel or quasi-perpendicular shocks. Some are easier to create in the lab than others. So I'll mostly focus on perpendicular shocks, so those that go across magnetic fields. Those turn out to be the easiest to create in the lab. There's different dissipation processes that happen in this shock front. And so you'll hear me talk about low or high Mach number shocks, which for our purposes, you can equate to subcritical or supercritical shocks. So whether or not this ion reflection is an important component in the shock physics. And I think that's probably good on that. And then I'll note again that these magnetized shocks are kind of the most prevalent ones that we see in the universe. So this, we heard a lot about supernova remnants earlier today. So this is a nice system for our case. It shows, for example, these two different qualitative types of shocks, these parallel and perpendicular ones, which you see in the form of kind of different phenomenological properties in terms of kind of sharper structures, more diffuse structures, as well as emission. Even though these are kind of very pretty to look at, most of our understanding of shocks actually comes from spacecraft data. I'll show a little bit of that because we can get very detailed kinetic scale information about what's going on in the shocks, whereas telescope observations tend to be pretty large scale or macro scale. And this is where I think lab experiments can help sort of complement these two regimes, maybe tying them together or focusing on areas that are difficult to get to just in the space case. Another reason that these supernova remnants are going to be interesting is it'll inspire kind of our approach to how we drive shocks in the lab that I'll come back to in a moment. So it turns out, this surprised me when I first learned it, maybe it'll surprise you, collisionless shocks have actually been studied in the lab for decades. The first experiments were back in the mid-60s, not long after they first discovered that these kinds of shocks exist. At the time, they were done using imploding wire arrays. So imagine you run a bunch of current through a plasma that generates this azimuthal magnetic field and basically gets crunched. And as this implodes inwards, that magnetic field can drive the plasma to superalfanic speeds and drive this collisionless shock. And they were successful in doing that. So this is a paper from 1965. It turns out the type of shock you create in this kind of system is not very relevant to astrophysical shocks. It tends to be too slow. It's basically subcritical. And this shock part, which is the front here, doesn't ever really separate from the piston part. And so if you want to look at kind of any shock physics, that's hard to do in this scenario. So that's how things stood for a long time, basically until the advent of high-powered lasers. And then there was sort of a new paradigm for how we can create collisionless shocks in the laboratory. So this was first proposed by Paul Drake at Michigan and only demonstrated about 10, 15 years later in a laboratory setting. So the idea here, and again, I'm going to focus on the magnetized case, is you've got some plasma threaded with magnetic fields, so you've created this somehow. We'll talk about a few different ways to do that. And into that, you put a target that you shoot with a high-powered laser. That laser drives this piston plume, which is this hot, dense plasma expanding very rapidly. As it expands, it sweeps out magnetic flux, and you get this sort of snowplow effect. And it's actually that magnetic front that then couples into the background, pushes on it, and accelerates it to supersonic speeds. And so the shock is actually in the background. The piston is just there to transfer energy from your laser through the piston into the background. But the shock is all in this background plasma. On the right here is just a PIC simulation, just showing the early stages of this 2D PIC simulation of the magnetic field, where you can see this magnetic cavity that forms this compression from the magnetic piston, and then it starts to launch the shock towards the end. So the first successful demonstration of this was only about 10 years ago on the large plasma device at UCLA. As the name implies, this is a large plasma device. This is about 1 meter in diameter, about 20 meters long. These purple things are magnets, so it generates an axial magnetic field. And the setup is exactly what I just described. So LAPD provides a magnetized plasma. Into that is this target, which is basically a rod of plastic that you shoot with a high-powered laser, drives this piston, and then that drives a shock into the machine. So this successfully demonstrated for the first time using lasers a quasi-perpendicular, so this is going across magnetic field lines, but subcritical, so relatively slow, about Mach 2 shock. And it turns out under these conditions, the machine is too small to allow the shock to really propagate out and do interesting things. And so you either need to go to a bigger machine, or you need to find another way to get more system size into your experiment, which is basically a denser plasma. It's hard to go to a bigger machine. There's not much larger than this in terms of just raw plasma volume. And so the approach here was to go to much denser plasmas, basically shrink everything down in dimensionless sense. And this was done on the Omega EP laser facility, which you heard a little bit about yesterday. So this is one of these very large laser facilities that we have in the US. And the concept is the same, just everything is on much smaller scales. So note this is only about 5 millimeters across. So you've got some coils to generate a magnetic field. You've got some targets that you're shooting with lasers. And basically through the choreography there, you can create some plasma, magnetize it, and then shoot your piston to launch the shock. And so this was used to successfully show for the first time high Mach number supercritical shocks. But the shock lifetime was too short to, again, allow this shock to separate from the piston. So again, you can't really do much with it. You can generate them, but then you kind of run out of experiment. And if you're curious why we have two running into each other, this experiment started as a reconnection experiment. And the shocks were kind of a serendipitous discovery within that that happened kind of before they collided. So if you take out this second one, that's a more accurate representation. This is probably a good point maybe to note sort of what plasma regime we're in with these kinds of experiments compared to what's going on in space. So this is a table with a bunch of numbers. On the top here, I've got in the first column this supernova remnant that I showed earlier. And then in the second column, this is our first LAPD experiment. So you can see, obviously, the plasma parameters are very different, as you might expect in a terrestrial versus astrophysical setting. And it's relatively large, almost a meter, relatively low density for our purposes as experimentalists in plasma, about 10 to 13, and relatively low field. And so moving to much higher densities allows us to go to much smaller scales, but we need much larger fields, and that's kind of the trade-off that you have to have in these experiments. But all of these, if you go down to the dimensionless case, are what I would say are kind of in the right regime compared to astrophysical settings. So, of course, we can't recreate an astrophysically, scaled shock in the laboratory, not at all scales, but on ion scales especially, we can do a pretty good job of matching key dimensionless parameters between the two in terms of things like Mach numbers or collisionality or system size. All right. And so, the bottom message here, I guess I want you to take away is, at least again in the non-relativistic case, we can approximately study these astrophysically relevant shocks with appropriately scaled experiments. Okay, so that's kind of the background on how we go about generating them. So what I want to do now is focus on a couple of different experiments that are highlighting some of the questions that we can start to ask now that we have the capability to generate these shocks in the lab. And this first kind of high-level question that I want to focus on is this idea of energy partitioning in these collisionless shocks. So what I'm showing here on the left is a plot of this temperature ratio. So electron to ion temperature as a function of different speeds. It's basically the same plot, just with different x-axes for supernova remnants and bow shocks. And I guess this is Saturn's bow shock as well. And then on the right is some data from the MMS spacecraft going through Earth's bow shock. And so kind of the take-home message here is, we've got this nice data of how these ratios, kind of evolve with speed. We have this great data from the spacecraft around Earth that give you very detailed information about how energy is being transformed going through the shock. But we don't really have a complete theory of what drives this. We have a lot of simulations, and a lot of people have done great simulation work on trying to get at this, but kind of the very nonlinear nature, non-equilibrium nature of shocks makes it difficult to kind of come up with an analytic theory here. So this is where I think lab experiments can help to sort of understand this. So what we've developed is a variation on what I showed you in terms of driving these shocks. So this is on the Omega 60 laser facility. So if you haven't don't know anything about Omega, it's actually a two-part facility. There's two very large laser facilities there. The earlier shocks I showed you were on this Omega P. This one's on Omega 60. Doesn't really matter for your purposes, but they're both big lasers. And into this, we stick a target that looks like this. The main pieces here is you've got some coils to generate your magnetic field. You've got a plastic target. That's going to be for our piston. And then I've got this proton backlighter here that I'll come back to. That's for diagnostics. And a gas jet to generate our backgrounds. That's the idea. And again, note the scale. This is only about 1 centimeter in size. So the idea is drive your coils, create a magnetic field. It's about 10 Tesla in our case, and quite uniform in the volume that we're studying. Fire this gas jet. So you've now filled this volume with, in this case, hydrogen gas, about this density. Shoot our drive beams at this target. Serves two purposes. Those drive beams generate a lot of X-rays that ionize your background gas, so you now have this magnetized plasma sitting here. And then they also drive your piston that's expanding off very fast. And so it's through this process you can drive something like a Mach 10 shock. And then we probe it. And so there's two main diagnostics that I'll highlight here. One is Thomson scattering. Basically shoot a laser beam through this interaction, and the scattered light tells you a lot of information about what's going on in that plasma, as I'll show you. And then another one is proton imaging, which I don't think has come up before in great detail, but the idea here is you've got a little capsule filled with deuterium and helium. You shoot a bunch of beams at that. It basically implodes in a little mini fusion reaction. and releases 2 sets of monoenergetic protons at 3 and 15 MeV. So they're isotropic, but you can use those protons traveling through your system here. They get deflected by the electromagnetic fields and create an image on a detector, and from that you can back out what the electromagnetic structure of your shock looks like. All right, so then just to summarize then kind of what we have going on here in terms of what we can measure in these kinds of experiments. So with something like the Thomson scattering, we can measure a lot of plasma parameters, things like density, temperature, flow speeds, and really, if you're careful about it, even the velocity distributions themselves of what's going on inside your plasma. From proton imaging, you're backing out electromagnetic structures. And then one that I won't show for this, but you also have potentially refractive imaging, which gives you kind of large-scale density structures. What did I do? I jumped to the end. There we go. Okay. So let me start with the proton image because it gives you a nice, pretty 2D image of kind of what this thing looks like. On the left here, this is a proton image. This is made by firing these 15 MeV protons through your system. So imagine the protons are going in and out of the page through the system. And it generates this image of this magnetic cavity and then leading shock feature as this thing is expanding out. So you see this dark region. So all the protons are being deflected out of that region because the fields are so strong and so strongly compressed. And they end up in this kind of white region right behind it. And so you can invert this field through some simple and not so simple inversion techniques to back out what the magnetic field profiles look like, and confirm that you're getting very strong magnetic compressions, for example, in your shock. Even more detail you can get out of these Thomson scattering measurements. So here I'm showing 2 example spectrum. These are the same spectra. They're broken over 2 spectrometers, so just note the different ranges in the wavelengths here. The details aren't super important. The EPW and IEW basically refer to different plasma waves, so electron plasma waves and ion acoustic waves that you're essentially scattering off of in your plasma, and that's where all this information is coming from. But just qualitatively, we can see as you go kind of from left to right, so this is streaked in time, so we're looking at one place in the plasma and watching as our shock goes by. And so we see initially the upstream pretty quiescent and not much changing. Then you see the shock pass. A lot of things change all at once. Then you go into another kind of quiescent region in the downstream behind it, and then it transitions into the piston at the end. So qualitatively, that's kind of what we're seeing. Quantitatively, you can go through and use the theory of Thomson scattering. You get something that looks like this spectral density that relates the spectrum to all kinds of plasma quantities. Note that it directly depends on these ion-electron velocity distributions. So that's why if you're careful about this, you can actually extract those directly. And so you can get things like density and temperature and flow speeds and whatnot from looking at all of these features of the spectrum, how wide they are, how far apart the peaks are, how they're shifted, that kind of thing. So if you do this and apply it across time as our shock is going by, you get an image that looks like this. And so this is showing the density on the top, the temperature on the bottom, and this is doing kind of what you'd expect if you're driving a collisionless shock. You've got your upstream density. It goes through a rapid compression and then into a downstream, and then it's transitioning to the piston at the end. The temperature is getting rapidly heating as you go through that, and then sort of stabilizing in the downstream. Black is the electron temperature, red are the ion temperature. There's a bunch of other dots in here. These are just kind of null cases. If you take out the magnetic field or you take out that ambient gas, it completely changes what you see. And so we see, really for the first time here, a fully developed collisionless shock that is well separated from the piston. So this is something that is now allows us to actually study useful shock physics in a laboratory case. We see, not surprisingly, very strong non-adiabatic heating of the ions. You expect that in the shocks. You see ion heating that's happening ahead of these compressions. So that's kind of consistent with the foot region that you'd expect if you have these reflected ions. And then if you look more closely at the electrons, we actually find that they appear to be anomalously heated, similar to what's observed in astrophysical shocks. So this is just showing some different pieces of an electron heating model. I should say that this work is all been done by my postdoc, Vicente. And so, if you look at, say, what collisions do or what adiabatic heating does and add all those together, you get this black curve down here compared to what we're measuring in the electron temperature. And so there's additional electron heating that happens in these shocks that's not accounted for that. Again, similar to what spacecraft have measured. And so if you put all that together and look at what our electron temperature and ion temperatures are, our ratio for our Mach number kind of puts us here, which is pretty good agreement actually with what we see in space data for these Mach numbers. Okay, so this experiment has been very good because the diagnostics have been very good for measuring things like shock heating. Ultimately, though, the size that I showed you, that 1 centimeter, is kind of the maximum size you can get at with this kind of laser facility. It's just very hard to go bigger because either you lose magnetic field and then your whole experiment takes much longer, or they just can't field anything larger inside the chamber. So if you want a bigger system, let's say you wanted to study faster shocks, or you want to let the shocks evolve even longer, you have to go to an even bigger facility. And there's only 2 choices for that, and for our purposes, the one we chose was the Z machine at Sandia National Labs. So if you're not familiar, the Z machine is the world's largest radiation source and pulse power device. So basically, this is a very dramatic picture. It doesn't normally look like that when you fire it, but in the center, there's a little tiny load, and you're running a huge amount of current through that to do something. In our case, I'll show you what we do, but it's basically 20 megajoules of stored energy. This is very similar to the National Ignition Facility, which is a laser facility that gets dumped out as about 20 megaamps of current. So using something like this, we can take advantage of the fact that the types of plasmas we create are now based on the loads, the wires that we're using rather than the lasers to make bigger targets. And so this is a recent thing that we have started. We use something called an exploding wire array. So imagine a lot of little wires wrapped around this central conductor. And so you run all this current up through these little wires. They come back down through the center. And with that much current, you're both generating an azimuthal magnetic field and also ablating plasma that gets evected off. So you have this now magnetized plasma. And what's nice about this wire array is the size of this magnetized plasma is only limited by the size of your wire array and some current considerations. So we can make this much bigger. We can make a much bigger plasma than we could with the laser experiments. And then off to the side, I've got another little target here that we shoot with the laser. So the piston part doesn't change. Lasers are still the best for driving very fast plasma flows to launch our shocks. But the wire array now gives us a much better plasma to work with. And here's just a fun 3D model just to give you a sense of what that looks like. Different types of diagnostics on this. I won't dwell too much on it, but I'm going to highlight this refractive imaging, so kind of large-scale density structures, and X-ray spectroscopy that we can do on a machine like this. So just to give you a sense of what this looks like, this is a shadow graph. Basically, we've shot a laser through our plasma, and those rays have been refracted by the density gradients, and this is kind of an image that we're seeing. So at initial times, you've got this piston flow that's coming out, and it's starting to lead to these refraction features. And as you go into later and later times, it expands out. And so from that, we have kind of a rough idea of how fast this is. This is a much faster expansion than we had in the laser experiments, mostly because the laser is much more powerful. And there's some background conditions. And then if we look at the spectroscopy, we have very nice spectroscopy. That's something that the Z is very good at. So you can get all of these spectral lines, and by fitting those spectral lines, you can back out things like the electron and ion temperature of your background plasma, and I should note that this is ongoing analysis, so this is subject to change. But our first pass at looking at these temperatures puts a ratio at about 0.04, which again for our kind of Mach number and this temperature ratio is sort of consistent with what you see in astrophysical systems. All right, I think I only have a few minutes left, so let me just say a couple of words about one other campaign that we're doing. So the previous two were focused on particle or on energy partitioning and especially shock heating. The other kind of big topic in laboratory experiments on shocks is particle acceleration. And so we are interested in this too in the context of quasi-parallel shocks. So I'm just showing here, it's on the left, this is kind of the standard model for how particles get accelerated, this diffusive shock acceleration. But in order to participate in this process, you need some sort of initial energization process that kicks particles up and allows them to bounce back and forth. So exactly what that process is again something that's somewhat debatable. On the right here, just examples showing both simulations and observations of particle acceleration between parallel and perpendicular shocks. And you can see there's quite a significant difference between the two. And so we are interested in, can we observe particle, especially ion acceleration from parallel shocks, and does that look very different from what you get from perpendicular shocks? So this is a pretty new project, so I'm not going to show too much results. I'll just highlight kind of how we're going to do it. This is done on the National Ignition Facility. So the problem with parallel shocks is they take much longer to form. So too long to form inside the systems that I showed you previously. You need a lot of energy to kick them up and a lot of space to let them expand. And really the only facility for that is the NIF, which is the world's largest laser. And so the idea there is to basically drive these parallel shocks or quasi-parallel shocks using a whole bunch of energy from the NIF laser beams and then measure the accelerated particles as they come out of the top of this experiment. So I think with that, let me summarize. So overall, we have made great progress. I'll speak as an experimentalist. Great progress in creating collisionless shocks in the lab using high-powered lasers over the last 20 years or so, to the point where we're now seeing basically the transition from just creating shocks, which is kind of the first step, to actually studying shock physics with these laboratory experiments. And again, I kind of highlighted mostly energy partitioning and shock heating, but there's a lot of work going on in the particle acceleration space, not just from us, but from other groups. You could imagine the next step after this would be to try and go into, say, more extreme conditions, maybe relativistic shocks. I don't think you could get there with the facilities that I highlighted. While there's a lot of energy in those systems, they tend to top out in sort of how fast you can drive those shocks, maybe a few thousand kilometers per second. And so if you really wanted to get into much faster regimes, I think you'd have to go to kind of ultra-intense lasers, the kind of things that were talked about yesterday that can create much more extreme conditions, but probably on much smaller scales. And so everything's probably going to shrink down again to an even smaller scale, but much faster, maybe much higher fields, that kind of thing. All right, so I think with that, I'm happy to take any questions.
Much beautiful results. Any questions?
Hi, Derek. They're really nice experiments. So with your results, can you compare them to simulations? Lots of people do simulations of shocks here. So when you look at the temperature ratios, is it what you expect, or is there something different?
Yeah, so I intentionally left out the simulations because we have such good data that we didn't have to rely on them. But we have run a bunch of mostly particle and cell simulations modeling these experiments. What we haven't done, I suppose, is run the kind of simulation that would bridge the gap between some astrophysical system and the experiments. That's maybe a to-do. But we can definitely replicate what we're seeing in laboratory experiments. Actually, I do have a backup slide. This is just an example. So we use the code PSC. We've heard a bunch of other codes. I don't think that one has come up yet. And this is just showing all the different components that are happening in these experiments. between the piston and ambient and the different components. And so we get very similar temperature ratios from these, but I think you would want to structure this to be more similar to some sort of astrophysical shock and make that connection. So that's a to-do. Yeah.
Lawrence?
Moving a little bit towards the astro part. If you go to the plot of the temperature ratio as a function of Mach number, one, I would say, still major astrophysical puzzle is the apparently separate line that you seem to be having, in the supernova remnant plot, right? So the data points that are red that go up to equipartition at intermediate Mach numbers. So you have a data point, I think, at 30, which is close to where you have this bimodality between solar wind. I don't know if you have any thought about,
So, I can't really comment. I can say that the Weibull-mediated shocks, which are at very high Mach numbers, they're kind of over here, ended up with a temperature ratio sort of here-ish, around 0.3. So we kind of have this and then way over here. The problem here, this is Mach numbers of about 100, is it's just tricky to match all of the experimental conditions to kind of go fast enough to get to that and still have it fit within your experimental constraints. So I wouldn't say that's impossible. That is, we'd have to be more clever, I guess, about how we set it up. Yeah.
Just a word of caution. The measurements just give you this plot. This is fantasy and this is fantasy, right? So in order to get the alphenic Mach number, you have to assume some kind of magnetic field, and nobody measures that magnetic field. So all they really know is the velocity.
So the astronomers just made up...
Yeah, pretty much.
They do look pretty similar, though. So.
Yeah, for the supernova. Yeah,
okay.
of course.
Okay.
For the supernova.
Okay.
Yeah. Yes.
Derek, can you go back to the tonsor scattering data? So I think if I remember, yes, the ion acoustic wave shows an asymmetry right there in the two peaks, and that asymmetry is associated to a current.
It can be, yeah.
Yeah. So is the case here? Did you look into that?
So we didn't really look deeply into the ion features for this study. That's I'm going to say that is future work because the ions are a more complicated analysis process than the electrons. But yeah, so this kind of asymmetry is generally very clearly associated with some sort of relative drift in the electrons, some sort of current. But yeah, we haven't looked closely at what that means or its impact.
Related to this, do you have both carbon and hydrogen in here, right? So what is the role of carbon, and how many Larmor radii of hydrogen and carbon do you have in the experiment?
In this experiment, so our background is all hydrogen. It's a hydrogen gas. Our target is plastic, so the carbon comes out of that at a ratio of, I think, 2 hydrogen to 1 carbon. So there is some carbon, especially in the piston. And in fact, if we go to try and fit this, the only thing that really works is if you have a 50-50 fraction between the carbon and hydrogen, which is kind of what you'd expect from the target. The rest of this is only consistent with fractions of carbon that are well below 10%.
But what's the Larmor radius of the carbon? I mean, it will try to penetrate into the hydrogen, right?
It's, what would it be? It's, I think the hydrogen, I don't know if I know it off the top of my head.
But just, and in terms of hydrogen Larmor radii, how many are in the experiment?
This one. It's I want to say it's on the order of 5 to 10 of the hydrogen ones.
Derek, what role, if any, does collisionality play in these experiments? Coulomb collisionality, this is.
Yeah. So one of the major constraints of how we run these is this balance between keeping it as collisionless as possible while shrinking down the sizes, making it denser, that kind of thing. So on ion scales, it's quite collisionless. So if you look at the ion-ion collisionalities, those mean free paths are very large relative to the system size. And so that's why on ion scales, we can be pretty confident that we capture those dynamics. On the electron scales, and you can kind of see that here, especially at the higher densities, I would say it's moderately collisionless or collisional, depending on how you want to look at it. So certainly in the upstream, it tends to be pretty collisional. By the time you get into the downstream, it's been heated up, it's pretty collisionless. So there's some transition in there. So the extent to which collisions play a role is something that we have to pay attention to. That's why when we went to this modeling of the electrons, that was a big part of it, is how much do collisions contribute to that heating. And it turns out it gets heated so rapidly that it doesn't actually play that much of a role. It goes pretty collisionless pretty quickly.
Thanks for this nice summary, this nice overview there. Earlier we were talking about, Arnaud was talking about solitary magnetosonic structures in subcritical shocks. Have these been seen in some of these experiments?
Some people might say that some of the stuff we have seen in experiments were solitons. I don't know how strongly I'd endorse that or dispute it.
Do you have a model of magnetic field compressions from the radiography? Because those horns will correspond to solitons. So if you
not for that experiment that I showed.
The density compressions correspond to magnetic compressions.
So I guess, let me see. Our gyro time is about a nanosecond. So this sort of whole downstream would be about 1 gyro time. So if you're getting these kind of bumps, it's potentially mixed into where the piston is.
Look at the radiography. Just bring it.
This guy.
Yeah, there is finite thickness to that thing.
These.
Right? The proton depletion regions.
I'm not sure. We haven't looked closely at that aspect.
Cool. All right. Any more questions? If not, let's thank Derek again.